Hello, and this time we're going to be talking about elastic collisions. Now remember, elastic collisions will always have some amount of rebound to them, as we're showing in this cartoon example. And elastic collisions specifically conserve momentum, which all collisions conserve, and they conserve mechanical energy, okay? Specifically the kinetic energy of the system, so both objects' kinetic energies, before the collision and after the collision. Remember that we can set the potential energy reference level anywhere, so as long as we set it in line with the collision, then we don't have to worry about potential energies before and after the collision. Okay, so just the kinetic energies is what we're looking at. And elastic collisions are relatively rare in nature. Most collisions at the human scale anyway lose at least a little bit of energy during the collision, but they're a good approximation to a lot of collisions that we see, and they do occur, albeit more at like the subatomic level and things like that in nature. Okay, so they're a good model to use for certain things that we'll see. And we have two tools that we can bring to bear when figuring out the various characteristics of the objects involved in a collision, predicting their future behavior, figuring out what was happening just before the collision, all of those kind of things. And I wanted to explore these tools a little bit more. So for conservation of momentum, the sort of general equation for these things looks exactly the same as it did with inelastic stuff, right? You have the two objects with their two momenta just before the collision, and then just after the collision you have their final velocities times their respective masses to give you the total momentum final after the collision and before the collision. Okay, so that all looks exactly the same as an inelastic collision. What's different is that in a elastic collision, you also have this additional tool that you can bring to bear. And this can get, problem solving with this can get a little bit messy, mostly because of these squares that are always running around in the kinetic energy terms, right? By definition, they have to be there. Okay, there we are. And you can do a few things here, right? Like you can cancel out all the halves because there's halves on everything to simplify things a little bit. But often it is simpler to deal with a separate relationship that comes if you take these terms and you group all of the second object terms and you group all of the first object terms, something like this. And then you factor these, right? So you pull out the, say, M1, and you factor this into V1 final minus V1 0 and V1 final plus V1 0. Okay. If you look at that, the cross terms cancel out, and you can factor it in this way. You can do the same thing over here on the left. And if you do that and then do a similar thing with momentum, you group the terms by the object they're associated with, you can make a substitution from the momentum equation into this. And what you end up with after all of that algebra, which is a little ugly, okay, but doable, is a much simpler equation to deal with under many circumstances. And that equation looks like this. Okay? You get all of the masses of the various objects canceling out of the equations you substitute back and forth between momentum and conservation of momentum and conservation of mechanical energy, and you end up with this equation, which tells you that, in words, the relative velocity of the two objects before the collision, which is this, right, is equal in magnitude and opposite in direction to the relative velocity of the two objects after the collision. Okay? That's kind of cool. Okay? And it's only true for elastic collisions. Okay? You see, elastic collisions is right up here at the top of the slide, right? So the thing that occasionally happens is people will see this tool and they will say, aha, this might be useful in my collision problem, while forgetting that it only applies for elastic collisions. Remember, we started in that little partial derivation I just did with the principle of mechanical energy, and we substituted from the principle of conservation of momentum, and only then, when we make those substitutions, can we get to this equation. If this doesn't apply, right, if we're in an inelastic collision, well then this also will not apply, okay? So be careful with it, but it is nice because we don't need to know anything about the relative masses of the objects, right? We don't need to know m1, we don't need to know m2. This equation automatically tells us that the relative velocity before equals the relative velocity after, albeit receding instead of approaching. This is often also used as a check. If you have a collision, you're not quite sure whether it's elastic or inelastic. If you know enough about the velocities, then you can tell whether or not it's elastic based on whether it conforms to this equation, right? If this is an equality in your hypothetical collision problem, then you know that that collision is elastic. And if it doesn't hold, if this is not an equality, then you have a situation where you know that the collision is inelastic. We looked at an example, if you're in my Physics 100 class or my Physics 200 class, we looked at an example of that in one of our lectures this week. And you'll see other examples of that pop up from time to time as we move through this portion of the course. All right, so that's elastic collisions. I'm going to probably do an example or two next, but that's the end of our discussion for now.